A snowball melts so that its surface area decreases at a rate of 5 square centimeters per minute. Find the rate at which its diameter decreases when the diameter is 9 centimeters. So this is an interesting problem because I never really thought about how quickly a snowball might melt, but it makes sense that the rate of change relates to the surface area, because the more surface area it has, the more of it is exposed to warm air, and the faster it might melt, whereas when it is smaller, there is less surface area, and so it might melt a little bit more slowly. So yeah, just an interesting thing. Maybe that's exactly how it works, maybe it's not, but it is what it is for the purposes of this problem. So let's try and figure things out. We are looking at the surface area, so we need the formula for the surface area of a sphere, and we're assuming it's a spherical snowball. I think that's a fair assumption to make. The formula for the surface area of a sphere is given by A equals 4 pi r squared. Now, this is a relationship between the area and the radius, but the radius isn't mentioned anywhere here. We are actually supposed to be looking at the diameter, and so we want to change this instead of a function of the radius into a function of the diameter. Now we know that the radius is half the diameter, so we can write this as 4 pi times half the diameter squared. So that's going to be 4 pi times d squared over 4. 2 squared is 4, and look at that, the 4's cancel. And so the area in terms of the diameter is just going to be pi times the diameter squared. Once we have that, we can differentiate both of these with respect to time, and that will give us the relationship between the rates. So let's differentiate both sides with respect to time. So that's d over dt of pi d squared. Now on the left, the derivative of the area with respect to time is just dA over dt. On the right, when we differentiate d squared, that's going to be 2d. And with the pi, that's going to be 2 pi d. But times dd over dt, that's the derivative of the diameter with respect to time. Silly notation, but we can manage. And so now, what do we need and what do we have? We want to know the rate at which the diameter is decreasing. So we want to know dd over dt. Do we know the diameter at this moment? We do. We're told the diameter is 9. And do we know dA over dt? Surely we do. It's decreasing at a rate of 5 centimeters per minute. So that's actually going to be -5, right? Because A was the area, and if the surface area is decreasing, that means the derivative is negative. So we've got that -5. If we want to get dd over dt alone, we've got to divide by this. 2 pi times 9 is 18 pi. So we divide both sides by 18 pi to get that derivative alone. So that gives us our dd over dt at that moment. And if we use a calculator to get an approximation, that's going to be -0.088. And this is going to be, the diameter is decreasing, so that's going to be centimeters per minute. So it's decreasing at a rate of 0.088 centimeters per minute at that moment. If we wanted to know how quickly it was decreasing at a different moment, we would just plug in a different number for the diameter and we'd be good to go.